Tonight, we drift through the largest map of the universe ever made. Not a photograph, not a flat image of where things appear when you look up. A three-dimensional map, a true record of where things actually are, how far away they sit, how they cluster and string together across distances so large that the word distance starts to feel inadequate somewhere around the third or fourth time you use it. The instrument that built this map spent 3 years sweeping the sky above the Arizona desert, night after night, gathering light from galaxies and ancient cosmic objects that had been out there, undiscovered in any catalog, for longer than the Earth has been solid. When the data finally came back and was processed, it contained 13.7 million objects. Most of them, the overwhelming majority, had never been individually recorded before. We're going to spend this night with that map, with what's in it, what it means, and what it quietly implies about how much of the universe we are still, despite everything, only beginning to see. There is no urgency here, no race to cover material. Just a long, slow drift through one of the most significant things our species has managed to build. So settle in. The map is patient. It has been waiting for billions of years already. It can wait a little longer. On the 14th of May, 2024, a collaboration of scientists published a paper. That sentence doesn't do it justice. Science papers get published every day, thousands of them, most read by a few dozen specialists, and then filed away into the long, quiet archive of things that matter but don't make noise. This one was different, though the people involved were careful not to oversell it. Scientists tend to be careful that way. They present the numbers and let the numbers speak. And these particular numbers were the kind that, once you understood what they represented, made a certain kind of quiet fall over the room. The paper came from the DESI collaboration, the Dark Energy Spectroscopic Instrument. Not a single team at a single university, but something considerably larger than that. Over 900 scientists, 70 institutions, 13 countries. The instrument itself sits at the Kitt Peak National Observatory, on a mountain in the Sonoran Desert in southern Arizona, at an elevation of about 2,000 meters, where the air is dry and dark and the seeing conditions are among the best on the planet. DESI had been operating since May of 2021. 3 years of clear desert nights, the telescope sweeping systematically across roughly a third of the entire sky, gathering light from objects so far away that the light itself had been traveling since before the Earth formed. When the data was finally processed, and processing a dataset this size takes time, takes computing clusters running for months, takes hundreds of people checking each other's work, the catalog contained 13.7 million individual objects. Galaxies, quasars, ancient structures in the fabric of the universe that no previous survey had reached or bothered to look for, or had the technology to find. 13.7 million things we had never formally seen before. Most people didn't notice. A few did, and for those few, the sky looked slightly different after that. Not in any way you could point to, but in the way that knowing something changes what you see when you look up. Before anyone could count 13.7 million galaxies, someone had to figure out how to measure how far away a galaxy actually is. That sounds like it should have been easy. It wasn't. For most of human history, the stars were simply points of light at an unspecified distance, close enough to see, too far to reach, and completely impossible to measure with any tool anyone had yet invented. You could say a star was bright or dim, or that it appeared in a particular part of the sky. You could not say how far away it was. The night sky, for all its grandeur, was flat, a ceiling of unknown depth beautiful and entirely unmapped in 3 dimensions. The person who changed that was not a professor. She was not given telescope time. She was paid 25 cents an hour to sit at a desk in a room at the Harvard College Observatory and measure stars on glass photographic plates. And the official title for what she did was computer, because that was the word in the early 1900s for a person who performed calculations by hand. Her name was Henrietta Swan Leavitt. She had joined the observatory in 1895, one of a group of women hired by the director, Edward Pickering, to do the painstaking work of cataloging the sky. The work was precise, repetitive, and enormously important. Measuring the brightness of stars, classifying their spectra, building the foundational database that astronomers needed to do almost anything else. It was also work that most of the men at the observatory considered beneath them. The women who did it were sometimes referred to, not kindly, as Pickering's harem. They worked long hours in near silence, bent over plates the size of dinner trays, and most of them are not remembered by history. Leavitt is remembered, because at some point in the early 1900s, while cataloging variable stars in the small Magellanic Cloud, a small companion galaxy to the Milky Way, visible from the southern hemisphere, she noticed something that nobody had thought to look for. Certain stars pulsed. They brightened and dimmed in regular cycles over days or weeks, and Leavitt noticed that the ones with longer cycles were consistently brighter than the ones with shorter cycles. The relationship was clean, almost too clean. A star that took 30 days to complete one pulse was intrinsically brighter than a star that took 10 days, and brighter by a predictable, measurable amount. This was not a minor observation. This was, though nobody fully understood it yet, the key to the entire universe. Because if you know how bright a star actually is, its true intrinsic luminosity, and you can measure how bright it appears from Earth, then simple geometry tells you how far away it must be. The dimmer it looks relative to how bright it truly is, the farther away it sits. Leavitt had found a class of stars that carried their own brightness information encoded in their pulse rate. Astronomers called them Cepheid variables, and they became the first reliable measuring tape for distances beyond our galaxy. Edwin Hubble used Leavitt's relationship in 1923 to prove that the Andromeda Nebula was not a cloud of gas inside the Milky Way, as most astronomers then believed, but an entirely separate galaxy, enormously far away. The universe, it turned out, was not one galaxy. It was billions of them. Every distance measurement in modern cosmology traces back through a chain of techniques, and near the base of that chain, holding everything else up, is the pattern Henrietta Swan Leavitt found while sitting at a desk in Cambridge, measuring stars on glass plates for 25 cents an hour. DESI's 13.7 million objects all have precise distance measurements. Those measurements exist because of a method that exists because of a relationship that one woman found by paying attention to something everyone else had walked past. She died in 1921, before Hubble published his findings, before anyone fully understood what she had given them. The cosmos held its silence, patient as it has always been, and she had listened carefully enough to hear something in it anyway. Here is the problem with mapping the universe. You cannot simply take a photograph and call it a map. A photograph of the night sky tells you where things appear, their position on the dome of the sky, their brightness, their color. What it cannot tell you is how far away anything is. A dim star might be nearby and faint, or it might be brilliant and enormously distant, its light thinned by the vast space it crossed to reach you. A photograph flattens everything into a single plane. It gives you the ceiling, not the room. To build a true three-dimensional map, a map that tells you not just where things appear, but where they actually are in space, you need a different tool entirely. You need to measure distance. And to measure the distance to a galaxy millions or billions of light years away, the technique astronomers rely on most heavily is something called redshift. The idea is rooted in something most people have experienced without thinking about it. When a train approaches, its horn sounds slightly higher pitched than normal. When it passes and moves away, the pitch drops. The sound waves are being compressed as the source approaches, stretched as it recedes. Light behaves the same way. When a galaxy is moving away from us, and in an expanding universe, almost all of them are, the light it emits gets stretched. Its wavelengths grow longer. On the spectrum of visible light, longer wavelengths sit toward the red end. So the light from a receding galaxy shifts toward red. The faster the recession, and the farther away the galaxy, the more pronounced the shift. Measure that shift precisely, and you know the distance. DESI was built to do exactly this, but at a scale nothing before it had attempted. The instrument uses 5,000 optical fibers, each one thinner than a human hair, mounted in a focal plane at the top of the male telescope at Kitt Peak. Each fiber can be repositioned by a small robotic actuator, a tiny motorized arm, to point at a specific target in the sky. Every 20 minutes, all 5,000 robots reposition simultaneously, each one locking onto a new galaxy or quasar, and the light from all 5,000 objects flows down those fibers and into spectrographs that spread each beam of light into its component wavelengths, like a prism, revealing the precise redshift of each source. 20 minutes, 5,000 objects, night after night for 3 years. Previous surveys had taken decades to build catalogues a fraction of this size. The Sloan Digital Sky Survey, which ran from 2000 to 2008 in its main phase, catalogued roughly 900,000 galaxy spectra over the course of years. And at the time, it was considered a landmark achievement in observational astronomy. It was. DESI surpassed it by a factor of more than 15 in less than a third of the time. But the number alone is not really the point. The point is what the number represents. Each of those 13.7 million measurements is not just a location on a flat sky map. It is a position in three-dimensional space, a point placed correctly in the actual volume of the universe, at the right distance, in the right direction. When you take all 13.7 million of those points and plot them together, what you get is not a photograph of the sky. It is something closer to an architectural drawing of the cosmos itself, a record of where the matter in the universe actually sits, how it clusters, how it strings together, how it leaves enormous regions almost entirely empty. No one had ever been able to draw that drawing at this resolution before. There is a particular kind of feeling that comes from looking at something that has never been seen in this much detail. Scientists describe it in different ways. Some call it humbling. Some call it clarifying. A few, privately, use a word that sounds less technical: beautiful. The map exists now. 13.7 million points of light, each one placed precisely where it belongs in the dark. Numbers this large have a way of sliding past the mind without landing. 13.7 million. You read it or hear it, and something in the brain registers very large and moves on. The specific size of the number doesn't actually arrive. It stays abstract, floating just out of reach of anything you can feel. So try this instead. Imagine you're looking at each of the objects in DESI's catalog. Not studying them, just glancing. 1 second per object. A single second to acknowledge each galaxy, each quasar, each ancient point of light that the instruments spent 3 years collecting. 1 second, then the next, then the next. At that pace, you would finish in a little over 430 years. You would need to start sometime in the 1600s, before Newton had published his laws of motion, before the first accurate measurement of the speed of light, before any human being had looked through a telescope powerful enough to resolve a galaxy as anything other than a smudge. You would need to sit with those objects, 1 per second, every second of every day, through every year that followed. Through the Industrial Revolution, through the invention of electricity, of radio, of flight, through the entire 20th century and everything that happened in it. Through every year of your own life and the lives of everyone you have ever known. And you still would not be finished today. That is not a metaphor for something vague. That is the specific arithmetic of what Desi catalogued in 3 years of desert nights. The cosmos held its silence, patient as it has always been, and 13.7 million is only the part we managed to reach. Somewhere far from here, a cloud of gas drifts in the dark. It has been drifting for a very long time. Longer than the Earth has been solid, longer than the sun has been burning. It moves so slowly that the word moves is almost wrong. It shifts, the way a sleeping body shifts, without intention, without direction, pulled by forces so gentle they barely register as forces at all. The cloud glows softly from within, not with the hard, bright light of a star, but with something quieter, amber, at the edges where dust catches and scatters what little light exists. A deep, muted violet in the thicker regions, where the gas is dense enough to hold color the way water holds color in certain deep, still places. And threaded through it all, dark lanes where the dust is so thick it absorbs everything, cutting long, slow curves through the light like the shadows of things that are not there. Inside those dark lanes, something is beginning. Not quickly, nothing here moves quickly. But deep in the densest part of the cloud, gravity is doing what gravity always does, pulling inward, drawing threads of gas toward a common center with a patience that has nothing to do with hurry. The gas compresses, heats very slightly, compresses further. At the center of one particular dark lane, a knot of matter glows with the faintest possible light. Tentative, almost invisible against the surrounding dark, the way a coal at the edge of a dying fire glows. Not brightly, not with any certainty, but steadily, with a quality that suggests it intends to keep going. It does not yet know what it will become. It has been here for 1 million years already, waiting for the pressure to tip past the threshold. It will wait longer still. There is no hurry in a place like this. There is only the slow, warm, patient accumulation of something that has not yet decided to begin. The cloud drifts on. The amber light shifts, almost imperceptibly, along the edges of a dust lane. Somewhere inside the dark, the faint glow holds. That single glowing knot, that one protostar in one dark lane of one nebula, is, in the context of what Desi mapped, almost comically small. Not unimportant. Nothing about a star being born is unimportant. But in terms of scale, that entire nebula, that whole vast cathedral of gas and dust that might stretch across 100 light years, would be invisible in Desi's catalog. Too small to register. A rounding error in a dataset built to map structures hundreds of millions of light years across. This is the thing that takes time to absorb about the universe. It is not just large, it is large at multiple levels simultaneously, each one dwarfing the last so completely that the previous scale ceases to feel real. The protostar dwarfs a city. The nebula dwarfs the protostar by a factor that doesn't translate into anything human. The galaxy containing that nebula dwarfs it by another factor entirely. And the structure DESI was built to map, the arrangement of galaxies across the observable universe, dwarfs the individual galaxy the way a city dwarfs a single grain of sand on one of its sidewalks. What Henrietta Leavitt's measuring tape eventually revealed, once Hubble and those who followed him began using it, was that galaxies are not scattered randomly through space. That was the assumption for a long time, that if the universe was large enough and old enough, the matter in it would be distributed more or less uniformly, the way dust settles evenly on a flat surface given enough time. But matter doesn't settle that way. It pulls together. Gravity, given enough time and enough matter to work with, creates structure. And the structure it creates across the largest scales of the universe is something nobody fully anticipated before they saw it. Galaxies cluster along thin filaments, long, faintly glowing threads of matter that stretch across hundreds of millions of light years. Where those filaments intersect, the density of galaxies becomes enormous, forming the most massive gravitationally bound structures in existence. And between the filaments, separating them, defining their edges by contrast, vast regions where almost nothing exists at all. Not sparse, not thinly populated, nearly empty. Silent, dark, cold volumes that can stretch for hundreds of millions of light years in every direction without containing a single large galaxy. The universe, at its largest scale, looks like a web. DESI's catalog is the most detailed map of that web our species has ever produced. And to understand what's actually in it, what those 13.7 million points of light are telling us about how the universe is built and where it might be going, we need to go a little deeper into what the map actually shows. The first time most people encounter an image of the cosmic web, they think someone has made a mistake. It looks too organized, too deliberate, like something drawn by hand rather than assembled by gravity over 13 billion years. Long, bright filaments of galaxies curving through the dark, meeting at dense, glowing nodes, trailing off into nothing at their edges. Between them, the voids, enormous, almost perfectly empty regions that occupy most of the volume of the universe while containing almost none of its matter. The whole thing has a quality that the word random doesn't come close to describing. It has texture. It has architecture. DESI's map makes this visible at a resolution and scale that no previous survey could achieve. To understand what you're looking at when you look at the cosmic web, it helps to go back to the very beginning, not metaphorically, but literally. In the first fraction of a second after the Big Bang, the universe was a hot, dense, almost perfectly uniform plasma. Almost perfectly uniform, but not quite. There were tiny fluctuations in density, regions that were, by an almost imperceptible margin, slightly denser than the regions around them. Those fluctuations were quantum in origin, meaning they arose from the fundamental uncertainty baked into the fabric of reality at its smallest scales. In the early universe, those fluctuations mattered. The slightly denser regions had slightly stronger gravity. They pulled surrounding matter inward. The matter that moved toward them left the regions between them slightly emptier. Those emptier regions then had slightly weaker gravity, which meant matter continued to drain away from them toward the denser regions. Over hundreds of millions of years, this process compounded. The slightly denser regions became galaxy clusters. The slightly emptier regions became voids, and the matter flowing between them, following the gravitational landscape like water following the contours of a hillside, formed the filaments. What DESI's map shows, in finer detail than any previous catalog, is the end result of that process playing out over roughly 13 billion years. The filaments are real structures, not statistical patterns in a random distribution, not artifacts of how we choose to look. Actual physical threads of matter, held together by gravity, populated by hundreds or thousands of galaxies each. The Sloan Great Wall, identified from earlier survey data in 2003, is one example. A filamentary structure roughly 1.37 billion light-years long, one of the largest known structures in the observable universe at the time of its discovery. DESI's catalog reveals structures at comparable and larger scales, mapped with far greater precision and depth. The nodes where filaments intersect are galaxy clusters and superclusters, the most gravitationally dominant objects in existence. The Coma cluster, sitting roughly 320 million light-years from Earth, contains over 1,000 individual galaxies packed into a region that by cosmic standards is relatively compact. It is one node among countless thousands visible in DESI's map, each one a place where the web pulled hardest and matter responded most completely. And then there are the voids. This is the part of the map that takes the longest to absorb. The voids are not merely the spaces between things. They are themselves structures, defined regions with measurable boundaries, consistent internal properties, and sizes that challenge the imagination's ability to form a picture. The Botez void, one of the largest known, spans roughly 330 million light-years in diameter. If you were somehow placed at its center and looked outward in every direction, the nearest galaxies would be so far away that their light would take over 150 million years to reach you. Inside, there are a handful of stray galaxies, far fewer than standard models predict should be there. That last point is not a minor detail. Standard cosmological models, our best mathematical descriptions of how the universe forms and evolves, predict that voids should be underdense but not empty. There should be scattered galaxies throughout, a thin population of structures that never quite got swept up into the filaments. In many voids, that's exactly what we see. In others, the interior is almost completely bare. The discrepancy is small in statistical terms. In physical terms, it is a question without a fully satisfying answer. Nobody has explained this to general satisfaction. There are proposals. The voids may have evacuated more efficiently than models predict, or the galaxies that should be there may be too faint for current instruments to detect, or something about the way dark matter behaves in low-density environments may differ subtly from our assumptions. None of these explanations fully accounts for the data. It remains one of those quiet places in the map where the lines don't quite connect, where the picture is almost complete but not quite, and where that small incompleteness points at something the science hasn't yet reached. The web is real. The voids are real. The questions they raise are real. And DESI's map is the clearest view we have ever had of all three. There are places in the universe where nothing has happened for a very long time. Not quiet places. Not places that were once busy and have since settled. Places where, as far as any instrument has ever been able to determine, nothing of significance has ever occurred at all. No stars formed here, no galaxies drifted through, no light passed on its way to somewhere else. The filaments of the cosmic web are so far away in every direction that they are not even visible. Not faint smudges at the edge of darkness, but simply absent, too remote to reach across the space between. This is one of those places. The temperature here is barely above absolute zero. Not the cold of a winter night, Not the cold of high altitude or deep ocean. Something far beyond those. A cold so complete it has no texture to it, no bite, no sensation at all. It simply is. The absence of warmth, settled and permanent, extending in every direction without variation. There is no sound here. Not because sound is being absorbed or dampened, but because there is nothing for sound to move through. No medium. No molecules close enough to pass a vibration between them. The silence is not an experience. It is a condition, like the temperature, like the dark. It does not press against anything. It simply occupies the space, the way the space occupies itself. Somewhere impossibly far in one direction, a faint smear of light sits against the dark. A galaxy, or a cluster of them, too distant to resolve into anything with shape or detail. It has been there for billions of years. It will be there for billions more. It is not moving toward this place. Nothing is moving toward this place. The void holds its emptiness the way old stone holds cold, completely, without effort, without the possibility of being otherwise. Somewhere even farther, in another direction, another faint smear, then nothing, then nothing, then nothing after that, stretching on in every direction until the distances involved stop translating into anything the mind can picture and become instead a quality of the darkness itself. A depth that is not frightening, not lonely in any human sense, but simply vast and still, and patient beyond any patience a living thing has ever needed to practice. The dark here is not the dark of a closed room, or a moonless field, or even the dark of deep space near a galaxy. It is its own category of dark, ancient and total, and in its way, complete. And the cosmos held its silence, patient as it has always been. Cataloging 13.7 million galaxies was not, strictly speaking, the point. It was a byproduct, an extraordinary one, the kind of byproduct that would have been the entire mission of any previous generation of telescopes. But DESI was built for something more specific than counting. It was built to measure something that has no color, no texture, no detectable presence of any kind. Something we know exists only because of what it does to everything else. It was built to study dark energy. To understand what dark energy is, or rather what we currently think it might be, it helps to start with what it does. In 1998, two independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees at the High Z Supernova Search Team, were measuring the expansion rate of the universe using a specific type of exploding star called a Type 1a supernova. These explosions are useful for cosmology because they all reach roughly the same peak brightness, which means you can use them as standard candles, objects whose true luminosity you know, so their apparent brightness tells you their distance, the same principle Leavitt established with Cepheid variables almost a century earlier. What both teams found stopped them cold. The universe was not just expanding, it was accelerating. The galaxies were not simply moving apart, they were moving apart faster and faster with each passing epoch, as though something was pushing space itself outward with increasing force. Something was counteracting gravity on the largest scales. Something was winning. Nobody had predicted this. It contradicted the prevailing expectation, which held that the expansion left over from the Big Bang should be gradually slowing as the mutual gravitational attraction of all the matter in the universe pulled things back toward each other. Instead, the brakes were off. The universe was running away from itself, and whatever was driving that runaway was invisible, undetectable by any direct means, and apparently everywhere at once. Cosmologists gave it a name: dark energy. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for its discovery. The name is, as physicists sometimes privately acknowledge, more confident than the understanding behind it. We don't know what dark energy is. We know what it does. It causes the expansion of the universe to accelerate. And we know roughly how much of it there must be for the observations to make sense. Approximately 68% of the total energy content of the universe appears to be dark energy. The matter you can see, stars, gas, galaxies, everything that has ever emitted or reflected light, accounts for roughly 5%. Everything DESI catalogued, all 13.7 million objects, is part of that 5%. The rest is dark. 68% dark energy, 27% dark matter, which is a separate mystery we will return to. 95% of the universe, by energy content, is something other than what we can directly observe. DESI was built to probe that 68%, not by detecting dark energy directly, which is not possible with any current technology, but by measuring its effects with unprecedented precision. The method involves something called baryon acoustic oscillations, usually shortened to BAO. In the first 400,000 years after the Big Bang, the universe was a hot, dense plasma, a mixture of matter and radiation so thoroughly coupled together that pressure waves moved through it the way sound moves through air. These waves traveled outward from slight overdensities in the early universe, the same fluctuations that would eventually seed the cosmic web. Then, when the universe cooled to the point where electrons could combine with protons to form neutral hydrogen atoms, an event called recombination, the plasma became transparent. The radiation decoupled from the matter, and those pressure waves froze in place. They left an imprint, a preferred separation distance between pairs of galaxies, encoded in the distribution of matter across the universe, like a watermark in paper. That preferred distance, about 500 million light-years, shows up as a subtle excess in the probability of finding two galaxies at that separation compared to slightly larger or smaller distances. It is faint. It requires enormous data sets to detect statistically. But it is real and measurable, and it functions as a standard ruler, a known physical scale against which you can measure how the universe has expanded at different epochs in its history. This is what DESI measured: 13.7 million objects at a time. By mapping the BAO signal at different redshifts, different distances, corresponding to different times in the universe's past, DESI can track how the expansion rate has changed over the last 11 billion years or so. And by tracking how the expansion rate has changed, it can test whether dark energy has remained constant throughout that time, or whether it has evolved. The answer that came back in 2024 was not the one the simplest models predicted. It was not wrong. It was not a definitive overturning of anything. It was subtler than that, and in some ways more interesting. The data hinted, with a statistical significance that caught the attention of the field, that dark energy may not be what Einstein thought it was. And that particular hint points toward a question that sits at the center of everything DESI was built to ask. While all of this was unfolding in the data, the cosmic web, the voids, the first hints about dark energy's behavior, DESI was also doing something else entirely, almost as a consequence of looking so far and so carefully. It was seeing the past, not metaphorically, literally. Light takes time to travel, which means that when you observe an object billions of light years away, you are not seeing it as it is now. You are seeing it as it was when the light left. An object 10 billion light years distant appears to us as it existed 10 billion years ago, when the universe was less than 4 billion years old, when galaxies were younger and more turbulent, when the large-scale structure we see today was still in the early stages of forming. Roughly 2.3 million of the objects in DESI's catalog are not galaxies in the ordinary sense. They are quasars, the most luminous, persistent objects in the known universe. A quasar is powered by a supermassive black hole at the center of a galaxy, consuming surrounding matter at such an extraordinary rate that the energy released outshines everything else in the galaxy combined. Sometimes by a factor of 100, sometimes by a factor of 1,000. The galaxy itself becomes almost invisible against the glare of its own center. The most distant quasars in DESI's catalog emitted their light when the universe was less than 1 billion years old. That light has been traveling for almost 13 billion years to reach the detector on a mountaintop in Arizona on a clear desert night. They are, in the most direct sense possible, windows into a universe we can no longer visit. A record of what existed before most of what exists today had formed. And they reveal things about that early universe that no other instrument can reach. The light from those quasars has been traveling for almost 13 billion years to reach us. And the fact that instruments like DESI exist to receive it, to measure it, to place it precisely in a map of the universe is something that still strikes the people who built them as quietly remarkable. If you've stayed with us this far into the night, you're exactly the kind of listener this channel was made for. A like helps us reach more people who need nights like this. And if you subscribe, something will be waiting the next time sleep doesn't come easy. The quasars kept their light for 13 billion years. We'll keep the videos waiting for you. There is a technique in astronomy that works something like reading a shadow. When light from a distant quasar travels toward us across billions of light years, it does not pass through empty space. It passes through gas. Thin, diffuse clouds of hydrogen drifting in the intergalactic medium. The vast, sparse material that exists between galaxies, in the spaces the cosmic web leaves behind. And as the quasar's light moves through each cloud, certain wavelengths get absorbed. The hydrogen swallows specific frequencies, leaving dark lines in the spectrum of the light that eventually reaches our detectors. Each cloud leaves its own mark. Each absorption line corresponds to a different cloud at a different distance, a different moment in the universe's history. By the time the light from a distant quasar arrives at a spectrograph, its spectrum has been marked dozens of times over, a record of every cloud it passed through on its journey, stretching back billions of years. Astronomers call this pattern the Lyman alpha forest. The name comes from the specific wavelength of light that hydrogen absorbs most strongly. In a quasar spectrum, those absorption features stack up so densely at high redshift that they look, when plotted, like the vertical lines of trees in a dense wood, hence the name. Each line is a cloud. Each cloud is a moment in cosmic time. The whole pattern, read carefully, is a history of how hydrogen, the most abundant element in the universe, was distributed across space in the early universe, long before most of the galaxies we see today had fully formed. DESI's quasar catalog extends this technique to more objects and greater distances than any previous survey. Where earlier instruments had a few 100,000 quasar spectra to work with, DESI has 2.3 million. The statistical power of that increase is not linear. It does not simply give twice the information of half the sample. It gives access to subtler signals, smaller fluctuations, correlations that would be lost in the noise of a smaller dataset. What those correlations reveal is something specific. The large-scale structure of the universe at high redshift. In the early universe, as traced by the Lyman alpha forest, matches the predictions of the standard cosmological model with a precision that is, depending on your perspective, either deeply reassuring or slightly unsettling. Reassuring because it means the model works. The physics we derive from observations of the nearby universe, from the cosmic microwave background, from decades of theoretical development. It predicts what we see when we look back 13 billion years. That is not trivial. It is a genuine achievement of human understanding. Slightly unsettling because the match is almost too clean in some places, and in others it frays at the edges in ways that are too consistent to be random noise. Small discrepancies, carefully measured, statistically significant enough that the people who found them wrote them down and flagged them for follow-up, rather than attributing them to instrument error or bad luck. Science proceeds, most of the time, not through dramatic overturnings, but through the patient accumulation of small things that don't quite fit. A line that sits a fraction of a percent outside the predicted range. A correlation that holds in one part of the sky, but weakens slightly in another. A number that comes back the same way from multiple independent measurements when the model says it should be different. DESI's quasar data contains a few of those things. Nothing that breaks the model, just enough to keep certain offices very quiet on certain afternoons while someone stares at a plot and tries to decide if what they're seeing is real. The answer, for now, is that nobody is quite sure, which is, in the language of science, one of the most interesting answers there is. Step back from the individual details for a moment. The cosmic web, mapped in 3 dimensions at unprecedented resolution. Dark energy, measured across 11 billion years of the universe's history through the frozen imprint of ancient sound waves. Quasars, 2.3 million of them, their ancient light carrying the absorption signatures of hydrogen clouds that no longer exist in the same form, tracing the early universe's structure in a way nothing else can reach. 3 different lines of investigation, 3 different physical phenomena, 3 different techniques for extracting information from the sky, and all 3, in DESI's 2024 results, point in the same direction. Not loudly, not with the kind of clarity that ends debates and closes textbooks, but consistently, quietly, in the way that a building develops a lean so gradual that you only notice it when you stand back far enough to see the whole thing at once. The standard model of cosmology, the framework scientists call lambda CDM, which describes a universe filled with cold dark matter and a cosmological constant that drives its accelerating expansion, predicts, with considerable precision, what the universe should look like, how galaxies should cluster, how the expansion rate should have evolved, what the BAO signal should measure at different distances, what the Lyman alpha forest should look like at high redshift. DESI tested all of those predictions simultaneously, with more data than any previous instrument had ever gathered. And the model held, largely. Impressively, in many respects. The basic architecture of our understanding of the universe survived contact with the largest 3-dimensional map ever made. But there are places where it held less cleanly than expected. Small places. Careful measurements, checked multiple times, that return values sitting just outside the model's predictions. Not by enormous margins, by the kind of margins that, in a smaller dataset, would be dismissed as statistical fluctuation. In a dataset of 13.7 million objects, Measured with the precision DESI achieved, those margins become harder to dismiss. They have a persistence to them, a stubbornness, and they converge, these small discrepancies, on a single question that has been sitting at the center of cosmology for over a decade, quietly accumulating evidence on both sides, resisting every attempt at resolution, growing slightly more insistent each time a new instrument adds its measurements to the pile. The question is simple to state. The implications of answering it in either direction are not. The question is this: we have two different, completely independent ways of measuring how fast the universe is currently expanding. Both methods are precise. Both teams are competent. Both have checked their work more times than most people check anything in their lives. The two answers disagree. Not by a little, not within the margins of error, by enough that one of them, or both of them in different ways, must be missing something. Something in the physics. Something in our model of the universe, either at its very beginning or in its current state, that we have not yet correctly accounted for. The name for this disagreement is the Hubble tension. And DESI's map, the most powerful cosmological dataset ever assembled, did not resolve it. It deepened it. In 1929, Edwin Hubble published a paper. It was not a long paper. It contained a scatter plot, a handful of data points, and a conclusion that restructured humanity's understanding of the cosmos more completely than almost any single publication before or since. The conclusion was this: galaxies are moving away from us, and the farther away they are, the faster they are receding. The universe is expanding. Not into anything. Space itself is growing, carrying the galaxies embedded in it apart from one another, the way dots on the surface of an inflating balloon move apart as the balloon grows. The rate of that expansion has a name. It is called the Hubble constant, usually written as h0, and it describes how fast the universe is expanding per unit of distance. Specifically, it is measured in kilometers per second per megaparsec, meaning that for every megaparsec of distance between 2 points in the universe, those points are moving apart at a rate of h0 kilometers per second. For decades, measuring this number precisely was one of the central challenges of observational cosmology. Early estimates ranged so widely that some values were twice as large as others, and the uncertainty had real consequences. The expansion rate determines the age of the universe, the size of the observable universe, the fate of everything in it. Getting h0 right mattered. By the early 2000s, it seemed like the field was converging. The Hubble Space Telescope Key project, led by Wendy Friedman at the Carnegie Observatories, spent years measuring Cepheid variables in nearby galaxies and arrived at a value of 72 kilometers per second per megaparsec, with an uncertainty of about 8%. The field exhaled. Progress had been made. Then, a few years later, a completely different method arrived. The Planck satellite, launched by the European Space Agency in 2009, spent 4 years measuring the cosmic microwave background, the faint afterglow of the Big Bang, the oldest light in the universe, dating from roughly 380,000 years after the moment of origin. The CMB carries encoded within it an extraordinary amount of information about the early universe, its temperature, its density fluctuations, the relative amounts of ordinary matter, dark matter, and dark energy. By fitting a cosmological model to the CMB data, you can calculate what the Hubble constant must have been in the early universe and extrapolate forward to predict what it should be today. Planck's answer was 67.4 kilometers per second per megaparsec. The local measurement from Cepheid variables, type 1a supernovae, and other distance indicators in the nearby universe kept coming back around 73. 67.4 versus 73, a difference of roughly 8%. That gap sounds modest. In the context of cosmology, it is not modest at all. Both measurements had been refined to uncertainties of only a few percent. The error bars no longer overlapped. The two numbers were not, within the limits of what either method could achieve, compatible with each other. The teams checked, then checked again, then checked in different ways, with different instruments, using different standard candles, different calibration methods, different statistical approaches. The gap did not close. Other independent measurements, using gravitational lensing, surface brightness fluctuations of galaxies, the sirens of merging neutron stars detected in gravitational waves, each new method added a data point, and the data points clustered stubbornly around one value or the other, leaving the gap exactly where it was. And then DESI added its measurements. 13.7 million objects. The BAO standard ruler applied across 11 billion years of cosmic history, in the largest dataset the field had ever seen, cross-checked against the Lyman alpha forest in 2.3 million quasar spectra. DESI's results, when they arrived in May of 2024, were consistent with the lower value, the Planck value, the early universe value, the 67. But they were also consistent at the edges of their uncertainty with something in between. And critically, they contained a hint statistically significant at roughly 3 sigma, enough to take seriously that dark energy was not constant, that it had been stronger in the past and had weakened over time, or had varied in some other way, in a manner the simplest version of the standard model does not predict. If dark energy is evolving, that changes the extrapolation. A different dark energy history produces a different predicted Hubble constant today, which means the gap between 67 and 73 might not be a measurement error on either side. It might be a sign that the model connecting the early universe to the present is incomplete, that something happened between the Big Bang and now that our current physics does not fully account for. Something we have not yet found. Something that, once found, will require rewriting parts of the story we tell about where the universe came from and where it is going. The building has been leaning for a decade. DESI looked at it carefully, from every angle it could reach, and confirmed that the lean is real. Here is the fact, stated plainly. When we measure the expansion rate of the universe using the early universe, using the light left over from the Big Bang, the oldest signal we can receive, the Planck satellite's exquisitely precise map of the cosmic microwave background, we get one number: 67.4 kilometers per second per megaparsec. When we measure the expansion rate using the late universe, using the nearby galaxies, the exploding stars, the Cepheid variables that Leavitt's relationship made measurable over a century ago, we get a different number, closer to 73. The universe, depending on which end of its history you use as your ruler, appears to be expanding at two different speeds simultaneously. That is not possible. There is one universe. There is one expansion rate, whatever it happens to be at this moment. The laws of physics do not permit the same process to produce two answers. When two precise, independent, carefully verified measurements of the same physical quantity disagree, it means one of four things. One measurement is wrong, the other measurement is wrong, both measurements are wrong in different ways, or the model connecting them, the framework we use to translate one epoch's observations into another epoch's predictions, is missing something real. Every serious cosmologist working on this problem today believes the fourth option is the most likely. The measurements themselves have been checked too many times by too many independent teams using too many different techniques to dismiss as error. The gap has been sitting there for over a decade, and it has not gone away. It has, if anything, become more precisely defined with each new dataset, sharper edges on the same stubborn disagreement. DESI's 2024 results did not close the gap. In some ways, they made its edges clearer. The hint that dark energy may be evolving, that it is not the simple, unchanging cosmological constant Einstein proposed in 1917, but something more dynamic, something that may have varied over the universe's history, could, if confirmed, point toward the missing piece. A different dark energy history would produce a different expansion history, and a different expansion history would alter the prediction the early universe measurement produces for today's expansion rate. The gap might close. Or it might, as more data accumulates, reveal itself to be pointing at something even stranger. New physics, a modification to general relativity, a property of the early universe that nothing in the current model anticipates. We do not know yet. What we know is this: the universe is expanding, and the rate of that expansion, measured with the best instruments our species has ever built, returns two different answers depending on where in cosmic history you look. And that disagreement, that stubborn, carefully measured, decade-old gap between 67 and 73, is currently the largest unresolved tension in all of cosmology. DESI measured it more precisely than it had ever been measured before. The gap is still there. It is worth sitting with that for a moment. Not with alarm, not with the feeling that something has gone wrong, that science has failed, that the ground beneath our understanding is less solid than we thought. That is the wrong reading of this. The right reading is almost the opposite. The fact that we can measure the expansion rate of the universe at all, that we can take light from exploding stars billions of light years away, and light from the oldest photons in existence, and compare two numbers derived from those utterly different sources, and find that they disagree by 8%, that is an achievement so improbable, so dependent on centuries of accumulated knowledge and decades of instrument building and thousands of individual careers spent in careful, patient work, that the disagreement itself should be understood as a sign of how far we have come. You cannot find a gap in a map you have not yet drawn. The Hubble tension is not a failure. It is a precision instrument pointing at something real. What that something might be is, as of 2024, genuinely open. There are several serious proposals, none yet confirmed, each with its own implications. One possibility is early dark energy, a brief period in the universe's first moments when dark energy was significantly stronger than it is today, driving a faster expansion that would shift the early universe predictions upward, closing part of the gap. Several research groups have explored this, and while the idea is consistent with some data, it struggles with others. It solves one tension while creating pressure elsewhere in the model, the way pressing on one part of a fitted sheet lifts another corner. Another possibility involves the properties of dark matter. Standard cosmological models treat dark matter as cold and essentially inert. It clumps under gravity and does very little else. But if dark matter has properties we haven't yet detected, if it interacts with itself or with radiation in subtle ways, those interactions could alter the early universe's expansion history in ways that shift the Hubble constant prediction. A third possibility, and the one DESI's data most directly hints at, is that dark energy is not a cosmological constant at all. Einstein introduced the cosmological constant in 1917 as a fixed term in his equations of general relativity, a value that did not change with time or location, a static property of space itself. If dark energy is instead a dynamic field, one that has a value at each point in space and time, and that value can change, then its strength in the early universe could have been different from its strength today. The DESI results, specifically the W0W, a parametrization that describes how dark energy's equation of state changes over time, place the measured values outside the range the cosmological constant predicts. Not far outside, but outside. This is the hint. This is what the quiet offices were about. None of this is settled. The statistical significance of DESI's dark energy results sits at roughly 2 to 3 sigma. Real enough to take seriously, not yet strong enough to claim as a discovery. In particle physics, the threshold for announcing a discovery is 5 sigma. Cosmology uses similar standards. 3 sigma is a raised eyebrow. 5 sigma is a press release. DESI's first data release represents roughly 1/3 of its planned total dataset. The full survey, when complete, will contain somewhere in the range of 40 million objects. When those additional measurements come in and are analyzed, the statistical significance of every hint in the current data will either grow or fade. The gap will either close or sharpen. If it sharpens, if the dark energy signal crosses 5 sigma, if the Hubble tension deepens rather than resolves, the implications extend far beyond any single number. It would mean that the standard model of cosmology, lambda CDM, is incomplete in a fundamental way. That something real and significant is happening in the universe that our current physics does not describe. That the next generation of instruments, the Vera Rubin Observatory, the Euclid Space Telescope, the Nancy Grace Roman Space Telescope, will be mapping not just the universe as we understand it, but the edges of our understanding itself. The map is the most precise we have ever made. It is also in certain carefully measured places, showing us where the map ends and the unknown begins. Rise above it all for a moment. Not quickly, not with any urgency. Just a slow, steady drift upward and outward, away from the plane of the galaxy, away from the disk where the stars are densest and the gas clouds glow, and the spiral arms trail their slow curves through the dark. Rise until the disk itself becomes visible as an object, a flat, softly luminous structure spread across the darkness below, its center brightening to a warm, dense core, and its edges thinning gradually into the surrounding emptiness. From here, the Milky Way is not the river of light you see lying on your back in a field on a clear night. It is something else, a shape, a structure, an ancient, slowly rotating collection of several 100 billion stars, seen whole for the first time, the way you can only see a city whole from the air. The spiral arms are faint from this distance. They do not stand out as dramatically as photographs suggest. The disk is more of a soft, diffuse glow, than a crisp pattern, with the arms visible as slightly brighter concentrations winding outward from the central bar. The bar itself glows warm and dense at the galaxy's heart, a region so crowded with old stars that the light they produce together has a quality different from the arms, deeper, more amber, the color of something ancient and compressed. Around the disk, at much greater distances, the halo drifts. This is the oldest part of the galaxy. The halo predates the disk itself. It formed in the earliest epoch of the Milky Way's existence, when the galaxy was still assembling from smaller structures merging under gravity, before the disk had settled into its flat, rotating form. The halo is populated by old, dim stars scattered sparsely through an enormous spherical volume, and by globular clusters, dense, roughly spherical collections of 100,000 to 1,000,000 stars each, gravitationally bound, orbiting the galaxy in long, slow elliptical paths that take hundreds of millions of years to complete. From this height, you can see several of them, small, faint spheres of concentrated light drifting through the halo in paths so slow they appear perfectly still. Each one is older than the disk it orbits. Some contain stars that formed when the universe was less than 2 billion years old, ancient beyond any framework that translates into experience. They have been circling the galaxy since before the Earth existed, since before the Sun ignited, since before most of the stars now in the disk were born. They drift in long, slow arcs, these ancient cities of stars. They do not hurry. They have never hurried. Their orbits are so gradual that a human lifetime represents a fraction too small to measure of one circuit, a rounding error in a journey that began before anything alive existed to observe it. Below, the disk turns. Above, the halo holds its scattered stars and its ancient clusters, patient and still, circling a galaxy they predate in orbits older than the planet you are resting on tonight. The whole structure drifts through space so slowly the motion is invisible from here. It simply holds, ancient and quiet and complete in the way that only very old things can be complete. Not finished, not static, but settled into themselves so deeply that the question of change seems beside the point. And the cosmos held its silence, patient as it has always been. The catalog exists now. It sits on servers, accessible to researchers at any of the 70 institutions that contributed to building it, and in a public release, available to anyone with the tools to work with data at that scale. 13.7 million entries, each one a row in a table that records, among other things, the object's position on the sky, its measured redshift, its distance, its classification, and the quality of the spectral measurement that produced all of the above. It is worth spending some time with what those 13.7 million things actually are. The largest single component is galaxies. Ordinary galaxies, in the sense that they are resolved collections of stars and gas and dust, gravitationally bound, ranging from small, irregular dwarfs to massive ellipticals containing trillions of stars. DESI's galaxy sample concentrates on two specific populations chosen for practical reasons. The first is luminous red galaxies, usually called LRGs. These are massive, old galaxies, ellipticals mostly, their star formation long since completed, populated predominantly by old red stars that give them their characteristic color. They are bright, which makes them detectable at large distances, and they are reliable tracers of the underlying large-scale structure, clustering along the filaments of the cosmic web in ways that are straightforward to interpret. DESI's LRG sample extends to redshifts of around 1, meaning it probes the universe as it was roughly 8 billion years ago. The second population is emission line galaxies, or ELGs. These are younger, more actively star-forming galaxies, their spectra lit up by the characteristic emission lines of ionized gas, hydrogen, oxygen, the signatures of vigorous, ongoing stellar birth. They are harder to model than LRGs, more varied in their properties, but they are detectable at higher redshifts, reaching back further in cosmic time. Together, the LRGs and ELGs give DESI coverage across a broad swath of the universe's history, allowing the BAO signal to be measured at multiple epochs rather than just one. Then there are the quasars, 2.3 million of them, ranging from relatively nearby to extraordinarily distant, the most remote emitting their light when the universe was less than 1 billion years old. Each quasar spectrum carries the Lyman alpha forest encoded in its absorption features, a record of the hydrogen gas distribution at every distance along the line of sight between us and the source. The quasar sample alone contains more information about the early universe's large-scale structure than any previous data set. And then there are the objects that don't fit cleanly. Every large survey finds them. Objects that fall between classification categories, whose spectra don't match the expected templates, whose measured properties sit in the gaps between what the instrument was designed to detect. DESI's catalog contains a small but carefully documented population of these. Sources with unusual spectral signatures, objects whose redshifts are ambiguous, or whose emission lines don't correspond to any standard template in the classification library. Some of these are almost certainly artifacts, instrument noise, contamination from nearby bright sources, measurement errors that will be resolved with better data. But some fraction of unusual objects in any large survey turn out to be genuinely unusual. New types of objects, or familiar types in unfamiliar states, or configurations of matter that don't have a well-established category yet. Science, at its edges, collects these quietly, flags them, returns to them later. The history of astronomy is full of objects that sat in the unusual category for years before someone looked closely enough to understand what they actually were. Pulsars were dismissed as interference before Jocelyn Bell Burnell recognized their regularity. Quasars themselves were called quasi-stellar objects for years because nobody was sure what they were. The name is a contraction of that uncertainty, preserved in the terminology long after the uncertainty resolved. Whatever is sitting in DESI's unusual population right now, waiting for closer attention, has a name that probably doesn't capture what it actually is. It will be looked at again. Someone will spend a late night with one particular spectrum, trying to make sense of a line that doesn't belong, and either find the error or find something new. That process, patient, iterative, mostly quiet, occasionally extraordinary, is how the map gets extended. Not in a single dramatic discovery, but in the slow accumulation of attention paid to the things that don't quite fit. The 13.7 million objects we do understand clearly are already the most precise description of the universe's large-scale structure ever assembled. The ones we don't understand yet are, in their way, equally valuable. They are the edges of the map. Somewhere far from here, two stars have been circling each other for longer than the Earth has existed. Not quickly. Their orbit is vast, the distance between them so great that the light from one takes years to reach the other. They move through that distance in a long, slow ellipse, each one feeling the other's gravity across a gulf that would take a human spacecraft centuries to cross. and responding to it the only way gravity permits, with patient, inevitable motion along a path that curves just enough, over just enough time, to bring them back to where they started. One star is warm and golden, not the sharp white of a young star burning hot and fast, but the deep, settled gold of something that has been at this for several billion years and has found its rhythm. Its light spreads outward in all directions equally, as light always does, reaching the other star after years of travel, arriving faint and cool by the time it gets there. The other star is cooler, slightly smaller. Its light leans toward the orange end of the spectrum, the color of late afternoon on a world that orbits it at the right distance. Between them, in the space that neither one fully owns, the light from both mingles without interference, gold and orange, ancient and steady, crossing each other in the dark without collision or consequence, the way two silences can occupy the same room. There are no planets here, or if there were once, they are gone now, scattered long ago by the slow gravitational dance of the two stars tugging at anything that tried to settle into a stable orbit between them. Just the two stars, and the enormous empty space they share, and the long, slow clock of their mutual orbit ticking in the dark. They have completed this circuit an enormous number of times. Each orbit takes thousands of years by human measure, which means the number of times they have circled each other since the solar system formed is a number without a useful comparison. They were circling each other before the first multicellular life appeared on Earth, before the oceans settled into their current shapes, before the continents arranged themselves into anything resembling what a map shows today. They will be circling each other long after all of that has changed again. The gold light crosses to the orange star. The orange light crosses back. Between them, the dark holds its cold and patient distance, and the two stars keep their ancient time. There is a version of this story where DESI's results came back and everything confirmed exactly what the standard model predicted. It would have been a satisfying outcome in one sense, a validation of decades of theoretical work, a confirmation that the cosmological framework built up over the second half of the 20th century was essentially correct. Some scientists would have quietly celebrated. Others, privately, would have been disappointed. Because a perfect confirmation, while reassuring, does not open any new doors. It tells you that you were right. It does not tell you anything you didn't already know. What DESI found instead was something more interesting and more uncomfortable, and ultimately more useful. The tension at the center of it all is the question of what dark energy actually is. And on that question, there are currently two serious positions in the field, not easily reconciled, both supported by reasonable evidence, both with genuine implications for how the universe works. The first position is that dark energy is the cosmological constant. This is the simplest explanation, and in science, simplicity carries real weight, not because simple things are necessarily true, but because a simple explanation that fits the data is preferable to a complex one that fits it equally well. Einstein introduced the cosmological constant as a fixed term in his equations of general relativity in 1917. Initially as a way to produce a static universe, which he preferred on aesthetic grounds. When Hubble showed the universe was expanding, Einstein reportedly called it his greatest blunder and removed the term. When dark energy was discovered in 1998, the cosmological constant was reinstated, not as a blunder, but as a genuine physical property of space. Empty space in this picture has an intrinsic energy density that does not dilute as the universe expands. It is constant, everywhere, at all times, a fixed property of the vacuum itself. This picture is consistent with most of what we observe. It fits the cosmic microwave background data. It fits the large-scale structure. It fits the supernova measurements within their uncertainties. It is, for the majority of practicing cosmologists, still the default assumption. The second position, the one DESI's results quietly nudge toward, is that dark energy is not constant, that it is instead a dynamic field, sometimes called quintessence, whose energy density changes over time and possibly over location. A field that was stronger in the early universe and has since weakened, or that oscillates, or that behaves in some other way that produces an expansion history different from what the cosmological constant would generate. The DESI team used a specific mathematical framework to test this, the W0WA parameterization, which describes dark energy's equation of state as a function that can vary with time. A cosmological constant has W0 equal to -1 and WA equal to 0, fixed, unvarying. DESI's measured values for these parameters, derived from the BAO signal across their full redshift range, fell outside that prediction. Not dramatically outside, but outside. The statistical significance, roughly 2 to 3 sigma, sits in the uncomfortable middle ground that cosmology knows well. Strong enough to take seriously, not strong enough to call a discovery. The field has been burned before by signals at this significance level that faded when more data arrived. And it has also watched signals at this level harden into genuine discoveries as datasets grew. Neither camp is claiming victory. Both are waiting for more data. What makes the situation genuinely interesting is that the two positions make different predictions for how other measurements should come out. If dark energy is the cosmological constant, the Hubble tension should eventually resolve through some systematic error currently hiding in one of the measurement chains. If dark energy is dynamic, its evolving strength over cosmic history could account for part of the tension, shifting the theoretical prediction toward the observed local value. The Vera Rubin Observatory, which began full science operations in 2025, will image the southern sky repeatedly over a 10-year survey, building a dataset for weak gravitational lensing and supernovae that will constrain dark energy's behavior with unprecedented precision. The Euclid Space Telescope, launched in 2023 by the European Space Agency, is conducting its own wide-field spectroscopic and photometric survey. The Nancy Grace Roman Space Telescope, NASA's wide-field infrared mission, will add further independent constraints. All of them are pointed in different ways at the same question DESI has sharpened. The debate between the cosmological constant and a dynamic field is not merely academic. It is a debate about the fundamental nature of empty space, about whether the vacuum has fixed properties or living ones, about whether the universe's fate is sealed or subject to change, about whether the physics we have is complete or whether something real and significant is still waiting to be found. DESI did not settle this debate. It clarified exactly what the debate is about and made the choice between the two positions more consequential than it was before. That is, in its way, a significant contribution. Not the answer, but a sharper statement of the question, which is often where real progress begins.
There is a comparison that comes up in certain conversations about the large-scale structure of the universe that tends to stop people for a moment. It is not a mystical comparison. It is not an argument for hidden meaning or cosmic consciousness or any of the things that sometimes attach themselves to science when the facts are striking enough to attract that kind of attention. It is a straightforward observation about geometry, about the shapes that emerge when matter organizes itself under certain physical constraints. And it is striking precisely because it is so concrete. The cosmic web, as DESI's map reveals it in greater detail than ever before, has a specific architecture. Matter concentrates along thin filaments. Those filaments intersect at dense nodes. Between them, large empty volumes occupy most of the total space, while containing very little of the total mass. The distribution of nodes, the places where the filaments meet and the matter clusters most densely, follows a statistical pattern that can be measured and described mathematically. The typical separation between nodes, the typical thickness of filaments, the distribution of void sizes. These are quantifiable properties of a specific kind of network. In 2022, Franco Vazza and Alberto Folletti at the University of Bologna published a paper comparing these properties to those of a different network entirely, the human cerebral cortex. Specifically, the network of neurons and the connections between them that constitute the structural basis of the brain. Their finding was that the two networks share measurable similarities. The clustering coefficient, a measure of how densely the neighbors of any given node are connected to each other, falls in a similar range for both. The degree distribution, describing how many connections the typical node has and how that number varies across the network, follows similar statistical patterns. The ratio of densely connected regions to sparse regions, the typical path length between two nodes, the overall balance between local clustering and long-range connectivity. In several of these metrics, the cosmic web and the neural network of the human brain return comparable values. To be clear about what this means and what it does not mean the universe is a brain. It does not mean consciousness is a cosmic phenomenon, or that galaxies think, or that the resemblance points to any shared origin or purpose. These are networks that form through entirely different physical processes on scales that differ by a factor so large the comparison barely registers as numerical. The cosmic web spans hundreds of millions of light years. The cerebral cortex fits inside a skull. One was shaped by gravity and dark matter and the expansion of space over 13 billion years. The other was shaped by genetics and electrochemical gradients and developmental biology over the course of months. What the similarity does mean is more interesting, in a quieter way. Networks that emerge from certain classes of physical processes involving local interactions, preferential attachment, the tendency of connected nodes to become more connected over time, and the tension between local clustering and long-range efficiency, tend to produce similar architectures regardless of the specific substrate. The cosmic web and the neural network are both solutions to a class of structural optimization problem, arrived at independently through completely different physics, and the similarity in their solutions reflects the similarity in the class of problem rather than any deeper connection between them. The universe in DESI's map contains roughly 100 billion galaxies in total, across the full observable volume. The human brain contains roughly 86 billion neurons. The numbers are close enough to invite the comparison, though the coincidence is almost certainly just that, a coincidence arising from the fact that both numbers are large in roughly the same way, rather than from any physical relationship. But there is something worth holding on to in this comparison, something that has nothing to do with mysticism and everything to do with what it means to be the kind of creature that can build DESI. You are made of the same matter as the filaments in the cosmic web. The hydrogen in your body was forged in the Big Bang. The carbon, oxygen, nitrogen, the heavier elements that make biological complexity possible, were made inside stars that lived and died before the sun formed and scattered into the interstellar medium that eventually collapsed into this solar system. You are, in a very literal sense, made of the universe's matter, shaped by the universe's physics, carrying in the architecture of your neurons a faint structural echo of the architecture of the cosmos that produced you. That is not a poetic observation, it is a physical one. The network in your head and the network Desi spent 3 years mapping are both made of the same fundamental stuff, organized by the same fundamental forces, separated by scales of space and time so vast they cannot be meaningfully compared. And yet, when you measure certain properties of their structure, you find the same numbers looking back at you from both directions. There is no explanation for that which satisfies everyone. There is just the observation, sitting quietly in a 2022 paper, waiting for someone to look at it carefully enough to know what to do with it. Every map has edges. Not the edges of the territory. The territory in this case extends far beyond anything any instrument has yet reached, and probably beyond anything any instrument ever will reach. The edges of what we manage to draw. The places where the surveyed region gives way to blank space, where the data thins out and the measurements become uncertain and eventually stop altogether. Desi's map has 3 of these edges that are worth being honest about. 3 things the catalog cannot tell us, not because of any failure of the instrument or the scientists who built it, but because of the nature of what was being asked. The first is dark matter. Desi's map traces the large-scale structure of the universe with extraordinary precision. The filaments, the nodes, the voids, all of it rendered in 13.7 million data points, each one placed correctly in 3-dimensional space. But the map is, in a specific and important sense, incomplete. It shows only where the ordinary matter is. The galaxies, the gas, the stars, the 5%. The structure those galaxies trace, the web they follow, the filaments they cluster along, the nodes they collect at, is not primarily shaped by the gravity of the galaxies themselves. It is shaped by dark matter. The cosmic web is, at its foundation, a dark matter web. Ordinary matter falls into the gravitational scaffolding that dark matter builds, accumulating where dark matter is densest, forming galaxies along the threads of dark matter filaments that were already there long before the first star ignited. Desi's map shows the galaxies. The dark matter that organized them into those positions is inferred, its presence required by the data, its distribution roughly calculable from the galaxy distribution, but itself completely invisible. Not faint, not dim, not detectable in principle with any current instrument designed to collect light, because dark matter does not emit, absorb, or scatter light at any wavelength. It interacts with ordinary matter only through gravity, and gravity, while universal, does not produce a spectrum you can analyze with a spectrograph. We mapped the shadow of the dark matter web. The web itself remains as invisible as it has always been. Nobody has explained what dark matter is, not to the level of identifying a particle, or confirming a detection in a laboratory, or connecting it to any other known phenomenon in physics. There are candidates, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and others, each with theoretical motivations and ongoing experimental searches. None has been definitively detected. The searches continue. The dark matter continues to organize the universe into the structures Desi mapped, while remaining entirely beyond direct reach. The second thing the map cannot tell us is whether the universe has an edge. Desi's survey covers roughly 1/3 of the sky and reaches back in time approximately 11 billion years. The observable universe, the region from which light has had enough time to reach us since the Big Bang, extends to a radius of about 46 billion light-years in every direction, a sphere containing an estimated 2 trillion galaxies. Desi mapped a significant portion of the volume within that sphere at higher resolution than any previous survey. But the observable universe is not the universe. It is the part of the universe we can, in principle, see. Beyond the edge of the observable universe, space continues, possibly forever, possibly curving back on itself, possibly structured in ways that have no analogy to anything within our horizon. Current cosmological models are consistent with a universe that is either spatially infinite or so large that its curvature is undetectable from our position within it. The data does not distinguish between these possibilities.
The question of whether the universe has an edge, a boundary, a far side, that question sits entirely outside what any catalog can reach, including DESI's. The third thing is what came before. The oldest objects in DESI's catalog emitted their light when the universe was less than 1 billion years old. The oldest light we can detect from any source, the cosmic microwave background, dates from 380,000 years after the Big Bang. Before that, the universe was opaque, a hot, dense plasma through which light could not travel freely. What happened in those first 380,000 years is accessible only through inference, through the imprints left on the CMB, through the theoretical machinery of early universe cosmology. What happened before the Big Bang, if before is even a meaningful concept when applied to the origin of time itself, is not accessible through any observation. Not through DESI, not through any successor instrument, not through any technology conceivable within current physics. Some theories propose that the Big Bang was not a beginning but a transition, a bounce from a previous contracting phase, or a quantum fluctuation in a pre-existing vacuum, or a collision between higher dimensional structures. These are serious proposals made by serious physicists. They are also, at present, untestable. There is no observational signature that unambiguously distinguishes them from each other or from a genuine beginning. The map starts at the Big Bang. What sits on the other side of that boundary, if anything sits there at all, remains one of those quiet mysteries that most textbooks skip, not because it is unimportant, but because science has not yet found a way to ask the question in a form that data can answer. Nobody has explained this satisfactorily. The theories exist. The imagination reaches. The data stops. And the cosmos held its silence, patient as it has always been. There is a place in the galaxy where nothing has happened yet. A molecular cloud, dense and cold and dark, drifting slowly through the spiral arm the way all clouds drift. Without destination, without hurry, pulled by the broad, gentle gravity of the galaxy itself, in a motion so gradual it barely registers as motion at all. It has been drifting this way for a very long time. Longer than the Earth has been here. Longer than the sun has been burning. In all that time, nothing inside it has changed in any way that would be visible from the outside. From the outside, it is simply an absence. A place where background stars disappear. Not suddenly, not with any clear edge, but gradually, their light dimming and then failing as the cloud's dust absorbs what would otherwise have passed through. You can find it only by noticing what is missing. A darkness within the dark, denser and more complete than the surrounding emptiness, defined by what it hides rather than what it shows. Inside, it is cold in a way that has no easy comparison. Not the cold of a winter night or a high mountain or a deep cave. A cold that comes from the near total absence of energy. Temperatures a few degrees above absolute zero, where molecules move so slowly their motion is barely distinguishable from stillness. The cloud holds this cold the way old stone holds it, completely, without effort. But deep inside, in the densest region at the cloud's heart, something has been happening for a long time without announcing itself. Gravity has been pulling inward. Not quickly, nothing about this moves quickly. But steadily, over millions of years, a slight overdensity at the center of the cloud has been drawing surrounding gas toward it, compressing it, heating it almost imperceptibly, drawing more gas in turn. The process compounds on itself so slowly that a human lifetime placed anywhere inside it would register no change at all. And yet, at the very center of this slow collapse, something faint glows in the dark. Not a star yet, not yet anything with a name or a category. Just a dense, warm knot of gas that has crossed some threshold the surrounding cloud has not, that is slightly warmer than the material around it, that glows with the faintest reddish light at infrared wavelengths that no human eye could detect without instruments designed for the purpose. It does not know what it is becoming. It does not know anything at all. It is simply warmer than before, and the gas around it continues to fall inward, and the warmth continues to build, degree by imperceptible degree, over timescales that have nothing to do with anything alive. The cloud breathes, if breathing can be something that takes millions of years. The dust lanes hold their slow, dark curves. The faint glow at the center holds too, patient and tentative, and entirely unaware that what it is doing has been happening across the universe for almost as long as the universe has existed. This same slow gathering, this same crossing of thresholds, this same first faint warmth in the dark that will, given enough time and enough gravity and nothing to interrupt it, become a star. It rests in the dark and waits for what it will become. DESI mapped 13.7 million objects. Each one is a real thing, a galaxy, spinning slowly in the dark, containing hundreds of billions of stars, each star orbited by planets we will never see, each planet subject to whatever physics applies at that distance, at that temperature, in that particular corner of the universe. Or a quasar, blazing with the energy of a supermassive black hole, consuming matter at rates that dwarf anything in the nearby universe. Its ancient light carrying the absorption signatures of hydrogen clouds that no longer exist in the same form. Or something in between, or something at the edge of a category, or something still waiting for a closer look. 13.7 million of them, each one placed precisely in three-dimensional space, the full catalog representing our best current description of where the matter in the observable universe actually sits. And yet, everything in that catalog, every galaxy, every quasar, every unusual object waiting for a second look, is made of ordinary matter. Protons, neutrons, electrons, assembled into atoms, assembled into molecules, assembled into gas and dust and stars and the rocky surfaces of worlds. The stuff that emits light, absorbs light, reflects light. The stuff that spectrographs can measure and catalogs can record. 5% of the universe by energy content. The other 95%? The dark matter that built the scaffolding the galaxies follow. The dark energy that is pushing everything apart at an accelerating rate that two independent measurements cannot quite agree on, sits entirely outside what DES cataloged. Not because DES failed to look for it, because it is, by its nature, beyond what any catalog built from light can reach. We mapped the 5% with more precision than has ever been achieved. We found hints in that 5% that point toward the behavior of the 95. We found a gap in two measurements that suggests something real is missing from the model that connects the universe's beginning to its present. We found a map of the cosmic web so detailed that the structures in it are now the most precisely located objects in the history of human observation. And we found, as every generation of astronomers has found, that the more carefully you look, the larger the unknown becomes. Not because knowledge shrinks with scrutiny, it doesn't, but because the questions that precision reveals are always larger than the questions it resolves. The map is the most detailed we have. The territory is still mostly dark. That is not a failure.
It is the condition of doing science at the edge of what is knowable, which is the only place science of this kind can be done. And there is something in that condition, in the combination of extraordinary precision and honest uncertainty, of the largest map ever made and the darkness it cannot reach, that feels less like a problem to be solved and more like a quality of the universe itself. Old, vast, mostly invisible to us, and patient in a way that makes all our instruments, for all their extraordinary reach, feel like the first cautious steps of something that has only just begun to look. There is something specific about being the kind of creature that does this. Not just the mapping, the knowing that the map is incomplete and doing it anyway. The full awareness, held simultaneously, that what you are building is the most precise description of the universe ever assembled, and also a description of 5% of what is actually there, and choosing to build it regardless, because 5%, mapped with enough care, tells you things about the other 95 that nothing else can reach. Humans have always mapped more than they could fully see. The Polynesian navigators who crossed the Pacific in open vessels read the ocean the way astronomers read spectra, not by seeing their destination, but by interpreting signals. The behavior of swells deflected by distant islands, the flight patterns of birds moving toward land, the particular color of water above a reef. They built mental maps of an ocean too large to hold in any direct view, from signals that required years of training to interpret correctly. And they crossed thousands of miles of open water to places they had never been, guided by an understanding of the ocean's structure that preceded any instrument designed to measure it. The early surveyors who walked the interiors of continents carried instruments of modest precision across terrain that had never been formally described. They placed their theodolites on hilltops and measured angles to distant peaks, and slowly, over years and decades, built maps accurate enough to stake legal claims and plan railway routes and understand, for the first time, the true shape of the land they lived on. They knew their maps were incomplete. They knew the instruments had limits. They mapped anyway, and the maps they built were the foundation on which every more accurate map that followed was built. DESI is the latest iteration of that same impulse. The instruments are incomparably more sophisticated. The distances involved are incomparably larger. The signals being interpreted, the redshifts of millions of galaxies, the absorption features of ancient quasar light, require a chain of theoretical understanding so long and intricate that no single person holds all of it. But the activity is recognizable across every scale of human history. There is something we do not fully understand. We build an instrument pointed at it. We measure what the instrument can reach. We sit with what the measurements reveal, including the gaps, including the discrepancies, including the things that don't fit the model we brought to the data. And then we build the next instrument. There is something worth noticing in this. Not a conclusion, not a lesson, just an observation about the kind of animal that does cosmology. We live for, at most, 100 years. The universe has been doing this for 13.8 billion. The structures DESI mapped were already ancient before the first organism on this planet developed eyes to see with. The Hubble tension is a disagreement between two numbers measured to a precision that took most of human history to achieve, about a process that has been running since before the Earth was solid. And we care about it, deeply, enough to build a 1,000-fiber spectrograph on a mountain in Arizona, enough to spend 3 years pointing it at a third of the sky, enough for 900 scientists to spend years of their lives making sure the measurements are right. There is no obvious evolutionary reason for this. It does not help us find food or avoid predators or raise children. The universe is indifferent to whether we understand it.
The gap between 67 and 73 kilometers per second per megaparsec will not close or widen based on how carefully we measure it. And yet, here we are, measuring it as carefully as we can. That fact, the sheer improbability of creatures this short-lived, caring this much about something this large, is, in its way, as strange and as worth sitting with as anything the map itself contains. There is a light that surrounds everything. Not a light you can see, not a light that responds to any human sense or registers on any instrument built for visible wavelengths. It exists at microwave frequencies, stretched so far from its original form by almost 14 billion years of cosmic expansion that the word light barely applies anymore. It is more like a memory of light, the faintest possible residue of something that once filled the entire universe with a brilliance no surface has ever experienced since. It comes from everywhere at once, not from a source, not from a direction, not from any specific place in the sky. From every direction simultaneously, arriving from the full sphere of the observable universe, a message sent from a time when the universe was 380,000 years old, and the plasma that had been everything finally cooled enough to become transparent, releasing in a single vast moment all the light it had been holding since the beginning. That light has been traveling ever since. Stretched by the expansion of space into wavelengths too long for eyes, too long for most instruments, it arrives at every point in the universe at every moment. A background so uniform and so old that it took decades after its prediction before anyone confirmed it was real. When Arno Penzias and Robert Wilson detected it in 1965 using a large horn antenna in New Jersey, they initially thought it was interference, perhaps pigeons nesting in the equipment, leaving residue that scattered the signal. They cleaned the antenna. The signal remained. It was the oldest thing they had ever detected, the oldest thing anyone had ever detected, arriving from a time so remote that the word ancient does not begin to reach it.
It is still arriving. Right now, as you rest here, that light is passing through you, through the walls around you, through everything. It is not stopped by matter, not absorbed by the air, not deflected by the planet beneath you. It passes through all of it at the speed of light, arriving from every direction, carrying its faint warmth. 2.7 degrees above absolute zero, barely above nothing, from a moment nearly 14 billion years in the past. It has no color. It has no brightness a human eye could register. It simply is, everywhere and always, a presence so old and so constant it has become indistinguishable from the silence it travels through. It was here before the first star, before the first galaxy, before the cosmic web had begun to form, before anything we have discussed tonight existed in any recognizable form. And it will be here long after the last star has faded and the last galaxy has dispersed, and the universe has stretched so far that any two particles of matter left in it will be too distant from each other ever to interact again. It surrounds everything. It has always surrounded everything. It arrives from everywhere at once, and it rests here too, in the quiet, patient, and ancient, and so faint it cannot be felt, drifting through the dark the way all things drift, without effort, without destination, simply continuing, as they have always continued, as they will always continue, long past the last moment anything is here to notice. Somewhere in the DESI collaboration's 900 scientists, there is a researcher who has lived with this data for 3 years. Not with the full catalog. Nobody holds 13.7 million objects in their head at once. But with a piece of it. A specific redshift range, perhaps, or a particular population of objects, or one of the statistical pipelines that converts raw spectral measurements into the precise distance estimates the map requires. She knows her piece the way a stonemason knows a particular wall. Not just its overall shape, but its grain, its texture, the places where the material behaves unexpectedly, and the places where it behaves exactly as it should. She is at a university, maybe Berkeley, maybe Portsmouth, maybe somewhere else entirely. The collaboration spans 13 countries. Her office is small. There are papers on her desk from 6 months ago that she keeps meaning to file. On the wall, there is a printout of a plot she made in her first year on the project, when a calibration error produced a pattern in the data that looked briefly like a genuine signal. It wasn't, but she kept the printout anyway because it reminded her what it felt like to think, for about 40 minutes, that she had found something new. On the night the collaboration submitted the 2024 paper, after the months of internal review, the repeated checks, the long video calls across time zones where people argued carefully about error bars and systematic uncertainties, and whether a particular choice of prior biased the dark energy result, she stayed at her terminal past 2 in the morning. Not to check anything. Everything had been checked. The paper was submitted. Her part was done. She stayed to look at the map. It takes a few seconds to render on screen at full resolution. When it comes up, it shows a slice through the three-dimensional catalog, a wedge of the universe with Earth at the narrow end and the full survey depth stretching outward, the galaxies appearing as small points arranged along the filaments of the cosmic web, the voids visible as the empty spaces between them, the whole structure laid out in a way that makes the large-scale architecture of the universe legible in a single image. She had looked at this image hundreds of times. She knew which features were robust and which were artifacts of the survey geometry. She knew where the data quality was best and where it thinned out at the edges. She had spent months working on the very measurements that placed those points in their correct positions. And she looked at it anyway, one more time, at 2 in the morning, in a small office in a city that was mostly asleep. 13.7 million points of light in the dark. She knew it was incomplete. She knew the dark matter holding those filaments together was invisible in the image. She knew the 95% was still out there, untouched by anything her instrument could reach. She knew the Hubble tension was still open, that the dark energy hint needed more data, that the unusual objects in the catalog were still waiting for closer attention. She closed her laptop and went home. Outside, the sky was the same sky it had always been. The same one Deci had spent 3 years studying. The same one Levitt catalogued from glass plates in a basement in Cambridge. The same one that has been receiving the light of 13.7 million objects for longer than anything on Earth has been alive. She walked home under it, and it held its silence above her, patient and unchanged, as it had always been, as it would continue to be long after any map we make of it has been superseded and the instruments that made it are retired and the scientists who built it have been gone for centuries. The cosmos held its silence, patient as it has always been. Somewhere in Deci's 13.7 million objects, there are almost certainly things nobody has looked at closely yet. Strange spectral signatures sitting quietly in the catalog, flagged as unusual, waiting for someone with the time and the right question to return to them. Objects whose measured properties sit just outside every established category, close enough to be filed somewhere provisional, but not close enough to be understood. Positions in the map where the clustering statistics behave slightly differently than the surrounding region, in ways that might be noise, or might be something the models don't yet describe. The catalog is published. The looking has barely begun. Every major survey in the history of astronomy has contained, somewhere in its data, something that turned out to be more than it first appeared. The answer was usually mundane: a calibration artifact, a known object seen at an unusual angle. Occasionally, it was not. Occasionally, the thing that didn't fit turned out to be real and new, and the beginning of a question that took years to properly formulate and years more to begin answering. The universe has been doing this for 13.8 billion years, producing structure at every scale, from the quantum fluctuations that seeded the cosmic web, down to the specific arrangement of matter that produced this planet, this night, this particular moment of quiet. It is not finished, neither is the map. If this night spent with the largest map of the universe ever made brought you some quiet, if the cosmic web and the ancient light and the patient, unresolved mysteries helped the day recede a little, we're glad you were here. There are more nights like this one. Other questions the universe is holding. Other corners of the cosmos worth drifting through slowly in the dark. They're waiting whenever you need them. Until next time, rest well. The map is still out there. All 13.7 million points of it, arranged in the dark in the precise positions they have occupied for billions of years, drifting so slowly through the expanding space between them that no motion is visible, no change perceptible across any timescale a living thing could observe. The filaments stretch between the nodes the way they have always stretched, long and slow and faintly luminous with the light of the galaxies strung along them. Each galaxy a soft smear of ancient starlight against the surrounding dark. Each one holding its position in the web with the patient gravity of 100 billion suns pulling quietly inward. Between the filaments, the voids hold their deep silence, cold and still, and so thoroughly empty that the emptiness has its own quality, its own weight, a darkness so complete and so undisturbed that the idea of anything moving through it feels like a disruption, like a sound in a room that has been silent for a very long time. The web turns, almost imperceptibly, on timescales that have nothing to do with anything alive. Somewhere in the halo of a distant galaxy, an ancient globular cluster drifts along its long, slow orbit, carrying 100,000 stars in a sphere so dense with light that from the outside it glows like a single, softly burning coal, patient and unchanged, circling a galaxy it was born before. Somewhere in a molecular cloud in a quiet spiral arm, gas drifts inward toward a center it will reach in 1,000,000 years, accumulating warmth so slowly that the warmth itself is a kind of stillness, a gathering that has not yet decided to begin. Somewhere between two galaxies, in the thin, cool medium of the intergalactic space the cosmic web leaves behind, hydrogen drifts in clouds so diffuse they are measured in atoms per cubic meter, so cold they hold no memory of the warmth that forged them, so still they will drift unchanged until something pulls them toward a denser region and the slow process of becoming begins again. The oldest light in the universe passes through all of it, through the filaments and the voids and the ancient clusters and the cold clouds, through the walls of the galaxies and the empty space between their stars, and the dark surfaces of all the worlds that orbit those stars in silence. Through everything,
without pause or absorption or any acknowledgement of what it passes through, arriving from everywhere at once, too old for color, too faint for feeling, carrying the warmth of a moment nearly 14 billion years past, through a universe that has spent all the time since growing steadily larger and quieter and more spread out and more still. It passes through here, too, through the walls around you and the air above you and the quiet that is settled over whatever part of the world you are resting in tonight. You are made of the same matter as the filaments. The hydrogen in you was forged in the first moments after the beginning. The heavier elements were made in stars that lived and died before the sun existed, scattered into the cloud that collapsed to form this solar system, gathered into the planet you are lying on, arranged by 4 billion years of chemistry and biology into the particular form that is resting here, right now, in the dark, under the same sky that holds the 13.7 million objects of the most detailed map our species has ever made. The map is out there. The filaments drift, and the voids hold their deep, cold silence, and the ancient light moves through everything at the speed that light always moves, and the cosmos continues in its vast and patient way, indifferent and extraordinary, old beyond any number that carries meaning, still and slow and quietly full of everything that has ever existed or will ever exist anywhere. Rest now. The map will still be there in the morning. The cosmos will still be there in the morning. Everything will still be there in the morning, arranged as it has always been arranged, in the dark, patient and silent, and waiting for nothing at all.